need to add is your contributions. Well, maybe I don't care.
I mean, I did step 1 through 7 as a 9-step process. Like,
that's for you to add. I'm not going to speak for other people. That and Sims units, that entire section, and we're done.
Yeah, I remember. I think I can't remember what day. It was Wednesday because the other 2 days were structured. And I was sitting on my computer. I'm like, you know what? If I get started on my dynamics project now, it's not going to be very good. So I sat and just did like the first 7 steps in a 9-step process in like 3 hours. I'm like, I'm uploading this to the Discord. Now we have something to start off with.
For some reason, the equation of motions got it right, except everything was shifted up by 1, where at between 0 and 1.5 seconds, my velocity is 1, not 0. I'm like,
yeah.
Okay, so I just told it, you know what? If you're going to shift everything by 1, I'm going to tell you shift everything by 1. I just told it -1 on all plots. And it's, oh, okay. And I'm like, sweet.
Yeah, MATLAB can be kind of funky like that sometimes.
Oh, it was like, oh, what's the integral of 0? Well, it's 0, but it's a constant. It's 1. And I'm like, what?
It's indeterminate.
Yeah, and I'm like, I was surprised that MATLAB didn't just assume 0, even without other initial conditions.
I just started the integral at
0 or 1.5.
Whatever.
It's like 1.47.
1.5659.
Oh, I thought it was. I'll check back mine.
Did you guys get?
It was around
Between
this
the analytical and numerical, did you guys get slightly different answers?
Like
in the
0.02.
decimals? Yeah,
Like
like
0.02.
something.
So the trick is also when you're doing it analytically, between each step of your piecewise, when you're integrating from your A to B, you get a constant. You have to set the 2 bounds equal to each other to solve for your constant. Otherwise, you will get mismatch. And it's not. It took me a while to figure it out. I'm like, wait, no, this is just integration. I'm dumb. Like,
Did you use the INT function for your integrals?
That's not going to work.
partly for the analytical solution. Yeah, I could do that. I did it by hand.
Honestly, we can just do that. If you were really desperate, you could just like screenshot your homework and put it in the. I mean, you could.
There is enough work that we will probably get.
If you were desperate enough on that project, the problem we literally did on one of our homeworks. You can you can just screen cap your like written work for that homework assignment and put it in the appendix, and boom, there's your analytical.
We have an analytical.
Okay.
I'm just saying, like, if you were really desperate.
Yeah. No, we didn't have analytical.
Yeah, no, I saw this step through.
I remembered my paper.
All right, I finished my homework. No one is online today, so let's begin.
I saw this.
Somebody's online.
Okay, so we don't have to have an appendix with a written. Like,
Okay,
No.
Julian is online. Can you hear me?
Yeah.
Okay. So for a moment, I'm going to mute you. But if you have a question, please unmute anytime. Okay. All right.
I can't.
So let's take in-class attendance video.
Like I'll lose my glasses.
Yeah, that's instant demand.
Yeah, that's it.
what's that?
Yeah.
Oh, my roommate's in a terrible scenario because literally this morning his girlfriend came in.
No, it's fine.
And he can't get counseling because, yeah,
First class medical.
yeah, and he's an AS major and he's pilot, so he can't go to counseling.
So I was actually. I was looking at your project phase 1. Project phase 1. Okay. This is the rubric of project phase 1 out of 30 points. So you submitted 2 tasks. Each task, if it runs, you get 5 points. That's fun. Is like what? Computing like a gravitational force. What is it?
Yeah.
Satellite force due to the gravitation of lots of different planets. So if I use it and if I get the correct value, you get 5 points. This one is like standard atmosphere.
Pass it.
Okay, so if it runs, it's 5 points. So if it runs means, okay, if it runs, spits out something without errors, 5 points. Result doesn't matter. So this is the result. So 15 points is kind of heavier because I'm thinking about pressure, temperature, density kind of separate. Because some of the teams say, well, the temperature is correct, but the pressure is a little bit off, the density is way off, pressure is a little bit off, stuff like that. Okay, so I'm actually going through the grading, but you know, what do you think? Did you guys do okay for this project? How many people actually said we did a perfect work? Please raise your hand. Nobody?
Certainly did something wrong, but I thought it was pretty good.
Pretty good means perfect. That means, hey, this can be used to compute standard atmosphere and also gravitational force for your other classes, let's say at, well, this is zero, but what other classes? I don't know.
Error 2.
Error 2.
Prop.
Yeah.
Propulsion is like
Yeah, do you,
all part 2.
so question, do you plan to use those software for those classes?
We actually had to rewrite them for those classes.
Yeah, but you are confident that we made up something meaningful?
Yeah.
We can use it.
Yeah.
I really need to see raised hand. Please raise your hand if you say, well, as an engineer, I did the job.
Yes.
Who's not raising hand? Who's actually? Jane's not raising hand? Or are you raising hand?
No.
No, you said no. That means you still want me to grade it by take a look at every detail. Or, well, we did the job, so give us full credit, whatever it is. Which one is it?
I'm not sure.
I need everybody's hand raised up if I go for, okay, I'll give you 30 blanket for everybody. That means I don't want to grade this. I give you 30 out of 30.
Do you have confidence in your work?
Raise your hand, John.
Okay. I'm not sure what you're asking,
So,
literally, do you have confidence in it? Yeah.
so if you actually says that, oh, you know, I don't think I think I did a poor job, so you should probably grade. Please raise your hand. Okay. I give you everybody 30 out of 30 for this. I don't even look at it. I don't want to grade it. I'm tired. So anyways. So everybody for phase 1 project, every team, you get 30 out of 30 as long as you submit it. Okay? So this is the starting point. And then starting from phase 2A and B, okay? Now I'm going to seriously evaluate. So this is the phase 2 evaluation. Again, 30 points, but task 1, if it runs 5 points, if it gives correct result, of course, it's obvious. Correct result is correct result. Okay, I can compare against my own result. You know, if it looks like a circular cylinder, it's correct. If it's not correct. So obviously, 5 or 0 situation. Anyways, so this is the evaluation for phase 2A, okay, which is flow of a circular cylinder. Phase 2B is a flow of a circular cylinder with a spin. Again, very similar thing. So this is out of 60 points because I'm going to take a look at more things like lift coefficient, CLE versus calculation CP pro. Those, well, we're going to cover that later. Don't worry about it. So again, so phase 2A, 2B, I'm going to evaluate your work based on this evaluation sheet. And then I'm going to probably post it online anyways so that you can take a look at it. Okay. So phase 1, you got 30 out of 30 to begin with. Okay. So you have some money in the bank to begin with. Okay? Question? Oh, you don't write this? You have a complaint?
No.
Okay, go ahead.
Do you have an idea of when you want to make phase 2A due?
Phase 2A is due right after I complete covering unit B3. Right after means right after, yes. So be ready for it. So we are here, page 5. Okay? So I don't know, 2 or 3 more class periods, we're done. And then all of a sudden, next class, okay, tiny project kind of thing. I don't know. I'm going to announce it as soon as I know, but I don't need to give you like a week or 2 weeks after completing B3. No, I don't think so. Okay. So let's just, you already have a team. Okay. So actually, what is my suggestion? As a team, you can finish up your homework, okay, on the go. In other words, when I complete some example in the class, you're supposed to work on the homework associated with, right? Okay. So start working on it, and then keep it up, and then try to educate each other in the team. It does not necessarily mean copy the wrong solution each other, no, but okay, discuss about it and then understand the mathematical details of each steps. In other words, this example problem B301 is the baseline of your task 1, of course. Okay, and then the other one, flow of a cylinder. Obviously, we want this one. This is baseline for task 2, I guess.
Yes.
Yeah, something like that. 2A or something. So stay focused on. It is very bad idea. Wait until I cover everything. Okay, let's go ahead start it. No, it's not a good idea. Okay. By the way, I forgot. Okay. Sorry. I was wondering why I cannot hear my voice. I was wearing mask. Sorry. This is better, isn't it? Okay.
Yeah.
Okay. Any question about project phase 2A? Of course, you have to finish up your homework first. Homework is very fundamentally important to do your project. Okay. So today we're going to start working on fast superposition. This is going to be, quite frankly, your task 1 of your project 2A. You probably need to do it anyways in MATLAB. Okay, so be aware of those things. So we are going to superimpose 2 elementary flow solutions. One is uniform flow with magnitude B infinity. So this is the magnitude of uniform flow. And then you're going to superimpose with the source. Magnitude of source is uppercase lambda. This is the flow, this is what is lambda represent? This is volume flow rate per unit width. So how much volume of flow you are going to produce at this mathematical singularity point called the source? Usually, you are going to put the source at the coordinate origin where, you are going to use either x, y coordinate. This is Cartesian. Or you can use r and theta, polar coordinate system. Either way is fine, but the coordinate origin is usually the location of this source. This is theta, this is r. So either way, polar or Cartesian. This, no. This is stagnation point, isn't it? No. Location of the coordinate is location of the source. So that means location of the source is here. Sorry. Okay. So this is coordinate origin, location of the source. This is where the source is located. Okay. Sorry about that. And then, of course, you can define polar coordinate also, not only Cartesian. Okay. So Cartesian or polar coordinate. Okay. So this is y, this is x. Okay. So be careful about that. When we try to do our mathematical analytical scheme, we are going to keep coordinate transform back and forth from Cartesian to polar, polar to coordinate. Now, in this case, original equation is given polar coordinate. Now, obviously, if you're dealing with the source, this is only a radial directional component of velocity exists. So it's easier to work on polar coordinate system mathematical sense. But sometimes when you plot the flow field, you have to convert everything into Cartesian. Now, in hand calculation, it's not easy, but you can do, okay, easily. Every data position can be transformed from polar to Cartesian, Cartesian to polar, either way. So let's begin with superposition. By the way, what is superposition? Anybody? Is that even English word? Do you use superposition like everyday language? Can you superimpose this food to that? Can you superimpose that sauce? I need a superimpose for that soup on top of this food. Superimpose. What is superimpose? It just add, mathematically speaking, addition. Addition of two elementary solutions together, because this is one elementary flow solution of Laplace's equation called uniform flow. This is the other type of elementary solutions of Laplace's equation called the source. The magnitude is B infinity and lambda. You just add them together to construct another varied flow field solution that actually simulates flow over leading edge of semi-infinite body. Okay, that's what we do. So everything is purely mass. So we're going to add them. Okay. So if you add them, psi is equal to B infinity R sine theta. Obviously, this is R and theta polar coordinate equation. And then plus lambda over 2 pi theta. Okay. So this is stream function of this flow field. This is the starting point. Okay. Starting point is your given stream function of this flow field, mathematically speaking, because somebody in the past actually solved those things and then ready for you. So you're going to just pick it up and combine those two. And first of all, what is the first step? Let's find out the velocity field. Okay. Velocity field in this case, of course, this is a polar coordinate, so you want to have a velocity in polar coordinate. B is equal to BR plus B theta E theta. Okay. Okay. So, of course, you know, BR can be given by polar coordinate system 1 over R d psi d theta. Okay. So you're going to do partial derivative divided by R. So this is 1 over R d theta over psi. Psi is B infinity R sine theta plus lambda over 2 pi theta. So can you do partial derivative? Partial derivative means that this is a differentiation with respect to theta only. So you're going to consider R as a constant. Okay. So if you do such a partial derivative, what is it? This is going to be B infinity cosine theta, and R divided by R is 1. So this is B infinity cosine theta comes up. The other one, this is going to be lambda over, okay, lambda over 2 pi divided by R. Okay.
Yep.
That's right. So this is going to be lambda over 2 pi R. This is the velocity in radial direction component BR. And then B theta. This is negative d psi dr. So this is going to be negative ddr of the same thing. So this is B infinity R sine theta plus lambda over 2 pi theta. Okay. So if you do such an integral, what happens? So this is
minus B.
This is minus B infinity sine theta, isn't it? Okay. The other one. This is 0 because this is pure function of theta. Okay. So this is it. So now you get velocity field. That's it. So you can describe the velocity just like this. So velocity V is equal to B infinity cosine theta plus lambda over 2 pi R ER minus B infinity sine theta E theta. This is velocity field. Here we go. Okay. So at this moment, you can do lots of things. Of course, you can draw streamlines. Stream lines you can draw instantly by given stream function. You're going to set some kind of constant that actually represent one equation streamline. So once you know the stream function, you can draw any number of streamline in the flow field that is contour lines of constant values of psi of the data field. Okay, MATLAB can instantly do that. And the next thing is at any location of r and theta, you can actually determine the velocity, magnitude, and direction. So you are completely given velocity field information also. Quite important. What is the next step, you think? I think usually the next step is I'm interested in location where the velocity becomes zero, something called stagnation point. Okay. This is something we are really interested in. Suppose if you're simulating the flow over some kind of body, stagnation point is usually comes in handy. So let's find out what is the stagnation point. That's the second step. So stagnation point, what's the definition of it? Of course, velocity gets zero. Stagnation point is basically, by definition, velocity becomes zero. That means both BR is zero and B theta is zero, both. Okay, so you come up with the two equations with two unknowns, R and theta, obviously. So starting from BR is what? BR is sorry. BR is B infinity cosine theta plus lambda over 2 pi r. This is BR. Let's set this is equal to 0. And B theta is negative B infinity sine theta, also equal to 0. So those are two equations, two unknowns, r and theta. So you're going to simultaneously solve this equation to determine the coordinate r and theta, which is essentially stagnation point. Okay, so solving these. So let's take a look at this equation first of all, okay? So this equation is B infinity sine theta is 0. What actually satisfies this equation? What is the value of theta actually satisfies this equation?
Theta equals 0 and pi.
Yeah, that's right. Theta equal to 0, pi, 2 pi, da. Then come to think about what is the theta? Theta is measured from here. So what is the actual theta, you think?
Pi.
Pi, okay, that's right. So this is a stagnation point. Theta equal to pi is something you choose. Okay. Be realistic, because you shouldn't choose something like a trivial solution. In other words, if you choose theta equal to 0, that means theta equal to 0. Stagnation point is theta equal to 0, and then it doesn't make sense. Okay. It's the inside of the body, which is trivial solution. You should avoid that kind of stuff. So this is the solution. Okay. So sometimes you have to take a look at the flow field and then choose that. Okay. So this solution, does it physically making sense, or just a mathematical solution? Trivial, physically doesn't make any sense, kind of thing. So this is the only choice you have. Theta equal to pi. Okay. Then let's just plug in theta equal to pi here to this equation. Okay. If theta equal to pi, then you can say B infinity cosine pi. What's cosine pi anyway?
1.
1 or
Minus
1 or minus 1? Lambda over 2 pi r is equal to 0. So cosine pi is negative 1?
Negative 1.
Are you sure? Okay, negative 1. So this is, okay, negative B infinity plus lambda over 2 pi r is equal to 0. So this actually solves for r. R is equal to
2 pi b infinity.
That's right, lambda over 2 pi b infinity, is that?
Yes.
Okay. Okay. So now we got stagnation point. Okay. So stagnation point location R theta is equal to R equal to lambda over 2 pi V infinity and theta equal to pi. Okay. Question?
So why do you put it in that format?
Yeah?
Why do you put it in the R theta format?
What? R theta format, what do you mean? This is coordinate.
Oh. So
Coordinate R theta is R equal to this,
Oh,
theta equal to.
yeah.
That's
So
coordinate.
for stagnation point, oh, it's a point. No.
This is the stagnation point, coordinate.
Yeah, it's a point.
That's right, that's a coordinate. Okay. Any other question? Go ahead.
Why don't you cross out the b infinity cosine? I to put -1.
Because cosine pi is negative 1.
Oh. Yeah.
Cosine pi is negative 1. That's what it is.
I thought like the whole, yeah.
Cosine pi is negative 1.
Yeah.
Period. Okay. Okay, so what? Is it causing some misunderstanding maybe? This is better? Maybe. I don't know. I would probably say, okay. I would probably say doing this is equal to -1. Is it better? Okay. All right, so let's just take a look at it. Okay, so flow field looks like this. So this is the coordinate, and you put the origin source, okay? And then you're going to superimpose with uniform flow. Magnitude is B infinity, magnitude is lambda here. So you're actually trying to simulate the flow field. It just looks like this. Creating this kind of body, extend to infinity, extend to infinity. And then you can draw any number of streamlines, just like that. Okay. And one important streamline I have to emphasize here. Since we understand this is the stagnation point, okay? Theta equal to pi, and then this distance measured from coordinate origin here, this is going to be lambda over 2 pi b infinity, okay? So this is something called, let's just put the capital R here. This is called node radius. Okay? And then next thing I want to do is I want to define a particular streamline equation that actually goes through the stagnation point. It's called the stagnation streamline. That's the third step usually. Okay, let me just take a look at third step. Third step. Something called stagnation streamline. This is actually quite important. This is actually a particular streamline that actually goes through the stagnation point. So you are going to draw a line like this, goes straight into the stagnation point. After you hit the stagnation point, what happens is you are going to divide into upper and the lower surface, okay? And then slide over this body shape. This is called stagnation streamline. Okay. Stagnation streamline is a streamline equation. Streamline that passes through stagnation point. How do you get that kind of equation? Anybody? Go ahead.
Plug in your stagnation point into your streamline function.
Oh, that's good. Very good. How do you know such a thing from like homework assignment
That was
you did?
literally part of the homework.
That's right. I appreciate that understanding. That's important. Okay. So you are going to go all the way back to this original equation of stream function. Plug in r and theta of stagnation point, then determine what kind of constant comes up with. Then set the cycle to that particular constant is the equation of stagnation streamline. Do you understand what I'm talking about? If you have like, that means you are in danger of completing, project. Go ahead.
No.
So, question?
No, never mind.
No, okay.
Thank you.
So once again, I'm going to pick up the equation of original stream function again. Psi is equal to b infinity r sine theta plus lambda over 2 pi theta. Then you're going to plug in this stagnation point r equal to lambda over 2 pi b infinity here, theta equal to pi. By the way, what's sine pi?
0.
Sine pi is 0. So psi is equal to 0 plus lambda over 2 pi theta equal to pi. Oh, pi cancels. Oh, okay. Pi and pi cancel. So you come up with the constant which is equal to lambda over 2. Okay, so you come up with the equation psi is equal to lambda over 2. This is the equation of stagnation streamline. Okay? This thing. Stagnation streamline equation. So if you plot using MATLAB, this equation, stagnation streamline, MATLAB plots this line and this line on top surface and this line on bottom surface. It is going to clearly define your body shape. Okay, stagnation streamline clearly defines your body shape if, important, if the stagnation point is located on the surface of the body. Stagnation point may not necessarily be always located on the surface of the body. You're going to find out in project 2B. Be careful. But the project 2A, don't worry about it. Stagnation point is located on the surface of the body. That means if you draw stagnation streamline, that is going to clearly indicate the body shape you are dealing with. Question?
Is it separated because it's spinning?
Oh, good point. You're gonna find out now, Sensei. He's
Yeah.
he's way ahead. Go ahead.
I'm a little confused. Back when we defined what a streamline is, we said it was a mathematical representation of the movement of a single fluid element. So how is
Not
that
the single fluid element, that's the path line. Streamline is a line defined in space where velocity is always tangent to the path. Now, in this case, we are going to completely ignore the boundary layer or viscosity. So, right here on the surface of the body, fluid is sliding over the surface, because there's no boundary layer, because this is ideal problem. So, since this is the velocity 0 point, stagnation point, and then since stagnation point is on the surface of the body, so this line actually represents the body itself. Because once you hit the 0 velocity point, the rest you have to slide over the body and throw it away. Okay, go ahead.
What is it the body of? Body of the
Solid body you simulate in mathematical data space. This is called half-Rankine body. Again, okay, listen, this is mathematical simulation, nothing real.
Oh,
Okay?
Okay.
Remember, you're engineers, so you probably want to deal with something real, but this is not something real. This is just a pure math. So this is the solid surface of the body you're trying to simulate. This is called half-Rankine body. Okay? So this is flow over half-Rankine body. Okay.
So it fully defines the body if it's.
Let me simulate, okay? What's the question, sorry?
So it fully defines the body if it's along the surface of the body.
That's the stagnation streamline.
Okay.
So free stream of one superimposed with source of, I don't know, source of, just a wild guess. Source is located at the coordinate origin, and then if I start drawing streamline is again line of constant value of psi in the data field. So this is going to create this kind of thing, right? So this is a contour line of constant value of psi, stream function of this flow field. And then, of course, you kind of begin to see, okay, well, I actually see the body in the flow field. This body is half-Rankine body. Why this kind of body is generated? Because there is a source here trying to reject incoming uniform flow based on the magnitude you preset. So depending on the combination between this magnitude and this magnitude, you can change the body shape, of course. Yeah, right.
When you're setting your source point and you're setting its strength, you're changing lambda, correct?
That's right.
Okay.
So strength of the source is a lambda.
It's just lambda.
Strength of incoming flow is B infinity.
B infinite.
So combination of those two actually changes the shape of the body. Right. So this is called flow over half-Rankine body, semi-infinite body of the leading edge. Go ahead.
Does doubling V infinity have the same effect as just having
Double it.
lambda?
Just to wait until we hit
No,
the
not
double.
double it. No.
Okay.
If you make the free stream twice as strong, is that the
Oh,
same?
yeah, of course.
as-
If the free stream is stronger, this is going to be diminished.
Yeah, I'm saying, are they linear? So if you
It's
have
not
it
linear.
twice as strong, is it the same as
It's
taking
not
half
linear.
of?
Well, you have to take a look at the mathematical expression point. So I guess, yeah, let's move on. Next page, we can find out. Yeah, you have to combine. Okay, so far we have finished. So far we have finished to this point. Okay, so you know the equation of stagnation streamline. You know the location of stagnation point. That's the only thing you know, but we can do more. Okay, so wait until then. You're going to find out, okay, so what is the combination of those strengths to determine the shape? In other words, nose radius R. Nose radius R. So this is nose radius, right? So nose radius is a function of combination of lambda and B infinity. So if you have a stronger B infinity and weaker lambda, nose radius is smaller, right? Okay. So those kind of things you can control. Yeah.
What's the units of lambda?
I think it's a volume flow rate per unit width. So how much volume of flow you produce per unit width, unit depth.
Okay.
Yeah. B infinity is of course velocity. Right. Yep.
So when we're generating those other green arbitrary streamlines for different arbitrary size, we just say, okay, it's going to pass through this r and theta, and give me a.
That's right. Yeah. So basically, those are. Well, if you mouse click right here,
yeah,
that's basically pick up the value of psi.
Yeah.
And then automatically connects the neighboring point of same value of psi. That's called contour line.
Okay.
There we go. You can do the same thing using MATLAB. It's a
Okay.
contour line. Okay. Am I answering all the questions you have? Keep that in mind. This is 100% math, nothing real. Okay. So this is what I'm showing here is this is mathematical data field. Okay, that's what you call theory of aerodynamics. 100% mathematics. Okay, we are just trying to simulate something similar to some physical flow field. Okay, but this is a starting point. Let's move on. Are you okay? You feel weird, but let's move on. You feel weird because you're an engineer. This is nothing real. Engineers dealing always with something real. That's why you feel kind of terrible. Okay. So next page, this is also another example that suppose, okay, you're going to superimpose uniform flow source and sink pair with the same magnitude, distance separated from the origin, location B and B. So superposition of three elementary flow solutions. Uniform flow source and same magnitude. It is going to create the flow field over oval. This is flow over Rankine oval. I can do that right here. Okay. So new flow. So once again, I'm going to put the free stream of magnitude of 1. And then I'm going to carefully set the source of magnitude 20, maybe 1 to 3 locations from the center here. And also sink is minus 20, which is 1, 2, 3 right here. Okay. superimpose of three things, and that's just a draw streamline. What happens? Okay, here we go. So now you have some kind of body formed up in the flow field. Can you see that? Okay. Well, it looks like this is a stagnation point. Here's another stagnation point. It's not quite circular shape, right? It's kind of distorted egg kind of shape. This is flow over Rankine oval. Go ahead.
We make the source and the sink equal from the same distance away from the origin just to make the math easy, right?
It's going to make a symmetric body itself.
Yeah.
Yeah. If you shift it to the different location, you're not going to create a symmetric body. It's kind of some different kind of shape, flow over some kind of different shape.
Sure.
Yeah. Go ahead.
If you choose your magnitudes for source and sink, does
Yeah.
that, will you get like a?
Again, it's going to
Something
create
similar.
some weird shape. You're going to kind of start manipulating your body shape, right? Okay. Well, now I'm going to create this kind of shape. And then, well, now I'm going to create this kind of shape. And then now you're getting there. Okay. Well, can I do continuously doing that to simulate the flow field over the cross section of a wing? Well, possible. It's like a trial and error kind of thing. You can never get exact shape anyways, though. So this is, I guess, very basic idea of, okay, can we use this technique to simulate the flow over some kind of cross section? The answer is kinda. We have a better technique. We're going to cover that later. It's called panel method. Okay. Because oftentimes you want to design your cross section and you want to simulate that exact shape you design. So the shape matters. You really want to exactly control the shape, right? Now in this technique, it's kind of limited. You can sort of control and simulate different shapes, but is that something exactly what you design? No, not really. Again, this is a mathematical tool to demonstrate what is the baseline mathematical theory in order for you to possible to do such a thing. So this is potential flow theory. So this is called flow over Rankine oval. Okay, that is this page. Okay. So this is again a very similar mass. Now in this case, this is the equation of stagnation streamline. In this case, psi equal to 0. So psi equal to 0 represent this line. Okay. So flow gets in, hit the stagnation point right here. This is stagnation point. And here's another stagnation point. And then slide over the body surface and then flow away. Slide over the body surface and then flow away. This is psi equal to 0. This is the equation of stagnation streamline. So this is a particular streamline that actually goes through the stagnation point. Go ahead.
So in solving for stagnation point, you'd have two solutions, like two non-trivial
Sometimes
solutions.
you have one solution of stagnation point. Sometimes you have two solutions of stagnation point. Suppose if this is the leading edge, trailing edge both exist. Right? The other one, trailing edge doesn't exist. So you only have one stagnation point,
right,
mathematically speaking. The other one is infinitely away.
Yep.
Okay. So, okay, so far. So this is your very first step of potential flow field analysis. 100% hand math. That's why you can use your MATLAB to do the same thing. So by the way, this is task 1 of your project 2A, right? Okay. So task 1, okay, starting from this page. This page actually sets up the stream function, finding stagnation point, and then stagnation streamline. We can do more. Let's move on, take a look at more. This is the example problem B31. This is very important page if you really want to do project 2A, task 1, whoever it is doing it. This is something you cannot miss. Anyways, let's take a look. So this is continuing from the previous superposition of uniform flow and source, okay? So superposition of uniform flow, strength B infinity, and source of strength lambda. Then, of course, we know this is a stagnation point coordinate, okay? Okay. So this is a coordinate of stagnation point. r equal to lambda over 2 pi b infinity, theta equal to pi. And then this is nose radius as we defined, okay? Okay, and then let's calculate something called ratio of little r over capital R. What is that? Little r is a coordinate location. Capital R is a this value. If you take the ratio of r over r, what does that represent? This is a body shape as a function of r and theta normalized by nose radius. That's what it means. Okay. How about CP? What is CP?
Pressure coefficient.
This is the pressure coefficient. In other words, you can compute how the pressure is distributed on the surface of the body. Let's compute those two. Okay. So starting point. Starting point is an equation of stagnation streamline. Equation of stagnation streamline, we found out psi equal to lambda over 2. This is a starting point. Okay. So remember, original psi is b infinity r sine theta plus lambda over 2 pi theta, okay, is equal to, let's say, lambda over 2. So this is the full description of the stagnation streamline equation. So you're going to start from there, and let's solve, let's just change a little bit. Okay, so this equation actually can be changed to b infinity r sine theta is equal to lambda over 2 minus lambda over 2 pi theta. Are you okay for that? And then from here, what is r equal to? R is equal to 1 over b infinity sine theta. Oh, I cannot finish up this thing. But anyways, I'm going to go as far as I can go. Lambda over 2 minus lambda over 2 pi of theta.
Didn't you factor out the lambda over 2 and make it simpler, so it'd be lambda over 2b infinity sine theta times 1 minus theta?
You have a point. That's right. So I'm going to do a little bit of trick. I'm going. I think you can kind of predict something what I'm going to do. So I'm going to basically do this: lambda over 2 pi b infinity. Okay. Pi over sine theta minus lambda over 2 pi b infinity theta over sine theta. Why did I do that?
So you can factor easier.
Factor easier. That's fine. Question, Robert?
No scratching.
You okay? So what I what I did was, okay, well, so what did I do? I multiply by pi, divide by pi. That's what I did, okay? Here we go. I multiply pi and divide by pi. You can do such a thing. Why am I doing that? Because I know that this is R. I know this is also R. I just wanted to do that. So this is R. Okay? This is also R. So it's really easy to factor out R. So this is going to be R pi minus theta over sine theta. Okay. So if you do little r over r, this is going to be pi minus theta over sine theta. Do you follow? So this is what I wanted to have. Now, one thing I have to do is I have to kind of flip-flop it. If you flip-flop r on r, this is going to be, of course, sine theta over pi minus theta. So it's the same meaning, but I kind of free-from. So we're gonna stop here, and then we're gonna continue next class, today is Friday,
Monday.
next Monday. So we're gonna continue this example program, and then see what kind of things we can get. We can actually plot the body shape. We can also plot the surface pressure distribution, CP. That is exactly task 1 is all about, project 2A.
So this is plotting the body shape, right?
This is going to be a normalized body shape, yes, you're going to try. Well, we're gonna find out on Monday. Question, yeah.
On the far right side of your equation, you have r is equal to pi minus theta over sine theta. That makes sense, but then you rewrite it as little r divided by big R. And then oh wait, never mind, I'm dumb. I forgot, I didn't
So this
see.
divided by big R.
Yeah, I forgot, I didn't see that you just divided by R and got rid of it. Yeah, because I'm like, wait, what happened? Then I realized, oh, parentheses are gone, R moves over the other side, and you're left with the inside one. Okay, that was me being dumb.
Okay? Any other question? We're gonna continue on Monday, okay?
I'll wait around Saturday and back again.